You know, light is everywhere. It literally defines our world. But what if I told you that light is constantly having these secret conversations with everything around us? And yeah, even inside of us? Let's tune in and decode that secret language.
Okay, so take a look at these three questions. At first glance, they seem completely random, right? I mean, a window, the Earth's climate, and your phone's screen. What could they possibly have in common? Well, stick with me because a single, really elegant rule of physics connects them all.
All right, so to get to that one big rule, we have to ask a basic question. What even is light? And the answer? Well, it comes from the wild world of quantum mechanics. And it's a little bit strange. Turns out it's not just one thing. So here's the deal. Physicists have this dual nature way of looking at light. Sometimes it acts just like a wave in a pond, with a frequency and a wavelength. But other times, it behaves like a tiny little bullet, a stream of massless energy packets we call photons. The key thing to get here is that both are true, and you need both ideas to really understand how light plays with the world.
And that brings us to the absolute heart of this whole thing, the one rule that pretty much governs every single interaction between light and matter. I like to call it the secret handshake. The scientists, they call it resonance.
Resonance is really just about matching frequencies. Think about tuning an old-school radio, right? You have to turn the dial to match the radio's receiver to the exact frequency of the station you want. It's the exact same idea here. For light and matter to really interact, their frequencies have to be perfectly in tune. So, what do I mean by a natural frequency? Well, pretty much every atom and molecule out there has a specific frequency it just likes to vibrate at. It's kind of like how a guitar string, when you pluck it, plays one specific note, or how these springs have their own natural bounce. Molecules have a rhythm, a beat that's all their own. That's their natural frequency. And this is it. This is the simple, powerful rule. If the frequency of a light wave comes along and it perfectly matches the natural frequency of a molecule, boom, secret handshake. The molecule absorbs that light's energy and the object looks opaque to us. But if the frequencies do not match, no handshake. The light is just ignored, it passes right on through, and the object is transparent. It's really that simple. And that one secret explains, well, everything we're about to look at. Okay, you ready? Let's take that super simple rule and scale it way, way up. We're going from why a piece of glass is clear to why our entire planet's atmosphere stays warm enough for us to live. This is where it gets really cool. You see, because our planet is warm, it's constantly radiating energy back out into space. But it's not glowing like a star. Earth gives off light at a much lower frequency, with a peak right around 10,000 nanometers. We can't see it. It's deep in the infrared part of the spectrum. You can just think of this as Earth's heat signature. And that leads to a huge question. If Earth is constantly trying to shed all this heat into the cold of space, why doesn't it just turn into a giant snowball? Something has to be stopping that infrared light from getting out. And, as you've probably guessed by now, it all comes down to resonance. Okay, let's look at the evidence. Here we have the infrared spectra for two different molecules. On the left, ethanol. On the right, carbon dioxide. Now, these graphs basically show us how much of Earth's heat can pass through these gases. If the line is high, the light gets through. If the line is low, it's getting blocked. Now, check out the difference here. The ethanol graph is kind of flat, right? It lets most of the heat pass right through. But look at the CO2 graph. See that massive dip? That right there is our secret handshake. It's a resonant frequency. It means the natural vibration of a CO2 molecule perfectly, and I mean perfectly, matches the frequency of the heat our planet is trying to get rid of. So the CO2 grabs that energy, it vibrates, and it traps the heat, warming our atmosphere. Isn't that incredible? That one simple idea scales from a single molecule to the climate of an entire planet. So now, let's bring it all the way back home, right inside your own head. So we all learned about rods and cones in school, right? The things in our eyes that let us see black and white and color. But what if I told you there's a third kind of light sensor in your eye? And get this, it's not for seeing at all, but it has this massive effect on how you feel and function every single day. Say hello to melanopsin. It's this special protein found in your retina. Its entire job is to detect light to set your body's 24-hour clock, what we call your circadian rhythm. It's the master switch that tells your body, hey, it's daytime, or okay, it's nighttime.
So if melanopsin is the switch, what flips it? You're already ahead of me. It's our old friend, resonance. Melanopsin is biologically tuned to have a natural frequency that is a perfect match for light with a wavelength of about 480 nanometers. And what color of light is that? Yep, it's blue light. So here's what happens. When blue light, whether it's from the morning sun or from your phone at midnight, hits your eye, bam, it resonates with the melanopsin. That sends this powerful wake up signal straight to your brain's master clock. That signal then tells your body to slam the brakes on making melatonin, the hormone that makes you sleepy. It basically resets your clock and keeps you wide awake.
And this isn't just some fun science fact. This discovery is so important, it's literally changing how we measure light and design our buildings. We now understand that the light your eyes use to see is totally different from the light your body clock uses to live. So think of it this way. We now have two ways to measure light. Photopopic lux is the old standard. It tells you how bright a light looks to your eyes. But melanopic lux is the new kid on the block. It measures the biological impact of light, specifically how much of that resonant blue light is present to hit your internal clock. So a room can feel bright to your eyes, but if it's low in melanopic lux, your brain is getting the signal that it's time to wind down. And this isn't just theory, it's already being put into practice. The WELL building standard, which is a huge deal in architecture and design, now actually specifies minimum levels of melanopic lux in offices and schools to make sure people are getting the right kind of light to stay healthy and alert.
So there you have it. We went from a pane of glass to the whole planet's climate to the back of your own eye. All of it explained by one simple idea: resonance. The secret handshake between light and matter is happening everywhere, all the time. So the real question is, now that you're in on the secret, what are you going to do with it?